Good afternoon from Geneva. As most of you know, the European Strategy for Particle Physics was adopted, the updated one, in 2020. And in this academic training lecture series, we want to provide a broad overview of the scientific and technological considerations that led to this strategy update. And today we discuss the experimental considerations that went into this strategy update. I'm very happy that Sphicas will present this lecture. He doesn't need an introduction, but let me still make a few comments. Paris got his PhD from MIT on the UA1 experiment, where he was a CERN scientific associate for 2 years. In 1990, he joined the CDF experiment as a Fermilab Wilson Fellow, and then as a member of MIT faculty, and he became a full professor at MIT. He joined CMS and he shaped the LHC physics of CMS since 1994. And in CERN, he's since 1997, and he has served here in various positions and responsibilities. He has also been a professor of physics in Athens since 2002. For the European Strategy of Particle Physics update, Paris has been the editor of the central physics briefing book. And without further ado, Paris, I'm very happy to have you here. Please start your presentation.
Thank you, Urs. Good afternoon, everyone, or good morning in case you're connecting from the other side of the ocean. So let me make sure that this crucial step that's called sharing actually works. And no, hold on. Sorry.
It worked already.
Voila. So here we are. So here is, I assume that you can see my slides, and now they should also be on full screen.
Yes.
Okay, excellent. Thank you. So, voila. This is the second part on experiment, as Urs just said. Keith Ellis did a great job in giving us the overview from theory yesterday. In keeping with the nature of these talks, which is academic training, I have tried to provide the panorama of the what measurements feed into the results. As you can imagine, because we're going to cover a lot of analysis space, a lot of physics space, at times things will get a little detailed, but this is, I'll try to keep the essence and the main message clear. So here's a breakdown for the talk. First, very few words on where we stand and what is the road to obtaining answers to the questions that are pending. And then we have three main items. The first one is the fundamental, is it really fundamental, scalar sector of the standard model, and the direct search for physics beyond the standard model. And here, the big questions are the couplings of the Higgs boson that we discovered as in the standard model? What about its self-coupling that, as you saw yesterday, determines the shape of the potential, and then eventually things such as whether the phase transition was first order or second order. And then, of course, the big issue is whether this object is fundamental, finally, or composite. Remember, we have no other fundamental scalar in particle physics. And then the other big item is direct searches for new interactions, new particles around or above the electroweak scale up to whatever the colliders will allow us to see. Then there is dark matter. And here the big one is basically the interplay between direct and indirect. And here I mean collider searches. I will not cover the astrophysics ones. I have some slides if you want, but I think already this is way too much material. And then finally, this is a bit of a heretic view, what I call the physics of flavor. Typically, you will hear about physics of flavor, meaning just the quark sector and then neutrinos being on their own. But I consider that the nature of the questions that are being asked, with the exception of the potential of the mass generation, which could be very different for neutrinos, they're basically addressing the same issue, which is the Y3. So in the quark sector, we have CP violation, rare decays of kaons and Bs, forbidden decays or extremely rare decays and so on. And then on the neutrino side, whether there are new sources, this would be a new source of CP violation. We hope to see it. A mass ordering of the neutrino state, the nature, and new particles or potentially new interactions hiding behind all of this. So where do we stand today? Well, we have the most successful theory ever. And this standard theory of particle physics, at this point, it makes sense more than anything else to basically study the newly discovered scalar sector. And the fact it doesn't just make sense, it's really our duty. So this is really the highest priority. And then we have 6 pieces of evidence that the standard model is either incomplete or part of an effective theory. As you already heard, experimentally, we have dark matter. It's the thing we know the least about, with an unknown mass range of 80 orders of magnitude. Neutrino masses, where the standard model gauge group allows for Majorana masses, so this would be something completely different with respect to all the Dirac fermions and so on. And this could explain their tiny values, albeit at the cost of a new unknown Majorana scale. And finally, there's matter-antimatter asymmetry of the universe, which has been an observable since the time of Mesopotamia, even prior to that, because it's nowhere near what we measure in CP violation experiments. We seem to live in a matter-dominated universe. Theory issues. There's the Electroweak hierarchy problem. Why is the Higgs so light? The flavor puzzle. Why 3 generations of quarks and leptons? Other than the fact that 3 was the sacred number of ancient Egyptians. Why so very different masses and mixings? Size of CP violation? Could this one way or another finally explain this matter universe? And of course, there's a strong CP problem, which is yet another vacuum issue like the Higgs is and like the Electroweak hierarchy problem, only this time it comes from QCD. And why is this infamous theta parameter so extremely small? Now, experimentally, what do we do to obtain answers to these? Well, we measure things. And when it comes to the physics of fundamental scalars and direct searches, well, colliders here have really the main word, where we have in sequence the LHC. Remember, we still have a run 3 before we go on to the high luminosity phase. And then there's the future colliders consisting of the triplet of the FCC, meaning EE, HH, and potentially EH. And then another doublet plus a singlet, you could see it as part of a triplet here, which is the ILC, CLIC, and then CEPC. This is in China, circular collider like the FCC. I'm not going to cover any of these because already Keith has addressed them. You know the bottom story, the bottom line story is that circular colliders have much higher luminosity. The linear colliders allow you to go more easily to the top threshold at 500 GeV or a TeV, something that circular EE colliders cannot do. And then finally, FCCHH is clearly the one that gets to the highest energies. The goal here is to understand the strangest of all elements of the standard model. And this is the Higgs, basically, that brings in a whole bunch of new interactions that basically we introduce by hand, essentially. There is a search for new particles and new physics phenomena. For dark matter searches, as we will see, there's a very large number of experiments that are aiming at detecting dark matter directly. And here there's direct detection, indirect detection, and matter-matter collisions. And there's some overlap between all 3, and there's even a sweet spot that if nature is kind to us, it would go and place dark matter, so we can study it in all three places. And then physics of flavor. Neutrinos, the main tool here is a complementarity between, there's the beams, June and Hyper-K in the US and Japan. The reactor program, Juno stands out, and then atmospheric, for example, Orca. Is there a CP violation in the lepton sector? Is there a PMNS matrix a la CKM like we have in the quarks? What is the mass hierarchy of the three neutrino generations? Is it normal or inverted? This is what will get answered here. And then dedicated experiments looking at neutrinoless double beta decay can decide on whether, can see whether this thing is Majorana. Quark sector, kaon and b hadron physics, both at the LHC, fixed target programs, and Bell 2 in Japan. Measure CP sources as precisely as possible, probe sacred, but also accidental laws, conservation laws, such as lepton number conservation, that recently there's even questions of universality and whether it's conserved or not, and probe the rarest decay mode. So that's it. So let's turn to the scalar sector and the direct searches. The big questions are, to what extent can we tell whether it's fundamental or composite? How well can the H boson couplings to fermions, gauge bosons, and itself be probed at current and future colliders? So this was answered at some 90% confidence level by Keith yesterday. And then I will add a few words on the FCC, HH. How do precision electroweak observables inform us about the Higgs boson properties and BSM physics? The Higgs potential, so this is part one. And then the second part is new interactions or new particles. Can we see thermal relic WIMPs, the ones that are still unprobed, and do we fully cover this area in future collider searches? And to what extent can we probe feebly interacting sectors? For the Higgs, this is here mainly for completeness of the slides, in case you ever come back to them. The biggest difference in H physics reach between EE and PP colliders comes from the fact that the lepton colliders can measure the Higgs width from the total cross-section for a ZH production. And that's because you basically, you can let the Z go completely undetected and go after the Higgs, or you can see the Z and then let all decay modes of the Higgs count in there. And that basically, so this is the strength of the EE program. And the hadron colliders were basically not directly sensitive to the Higgs width, as discussed already. There are two ways of depicting this. One is the Kappa frame. This is very easy to understand because it's essentially, you probe any deviation from the standard model because of some theory. You say, I know that the coupling, the effective coupling of the tau, the Higgs to the tau, is no bigger than 1.3 times that of the standard model. So that's easy to digest. The problem with this one is that the H couplings, there are some limitations to this, and this is that the couplings keep the full helicity structure of the standard model, where a standard model effective theory doesn't, because it allows for all possible interactions and spin structures and helicity structures. And then the other part is that the Kappa framework is blind to the power of polarization, where SMEFT is not. So, take-home message is that the invisible width is constrained directly at all future colliders, and the untagged width, meaning here, if you look at the total width of the Higgs and take the standard model one and you subtract what you don't see, which is the invisible and then the untagged. The untagged is basically H going to XX, includes BSM decays and rare standard model decays. So this you get very accurately, as was discussed already. This is only for completeness of the slides. What happens, however, for the grand summary, or for all the, sticking to the Kappa framework simply because it's easier to understand. Otherwise, you have this dizzying set of bars that you don't know how to interpret. If you look at how well we're going to measure the fraction with respect to the standard model values, you see that the ultimate project here, which is a combination of the FCC, EE, EH, HH, gives you sub% values on every one of these couplings. And even more is that the combination of the EE and the HH gives us also the best limit on the invisible branching ratio of the Higgs, of a tiny number that you see here. Take home message, and then we move on to the main part of the talk. All EE colliders achieve major and comparable improvements in the first stage, okay, compared to the HLLHC. Basically, at least half of these couplings improve by a factor of 5 or more, and one can get the WZ effective couplings and the invisible one down to 3 per mil. A model-independent total cross-section measurement gives us the width and the untagged branching ratio. And there's a clean environment to study H if and when anomalies are seen to understand underlying physics. That's it. Now, one thing to complete the picture is that EE colliders, for example, the FCC-EE has a program to run at the Z peak and collect a very, very large number of events. And on the other end, there's a program to perhaps get the FCC to go up to the 2 top threshold and above at 500, well, at the 2 top threshold only, and the ILC and the click that can actually get us to 500 in the TeV. So what do we learn from that program? Well, first of all, the top mass, which now one can measure from a threshold scan, and this is just a figure of what would be doable at click. You see the center of mass energy here. This is a 2 top mass, and you see the turn on, and that allows for a very accurate measurement. Remember that currently the top mass is unknown by about 400 MeV, and the goal of this program would be to get us down by an order of magnitude to 25 MeV. Notice that already just a theoretical uncertainty is 40 MeV out of alpha S, and this much more from higher orders. However, both of these numbers would decrease from running on the Z-pole. Speaking of the Z-pole, here is the number of events that one would get, for example, at the different collider. Here's the FCC-EE. Here's the Chinese electron-positron collider. And you see that one gets to basically 5, 10 to the 12 Zs. If one translates this into electroweak precision observables, you see that the mass of the Z could actually go down by more than an order of magnitude. The mass of the W could go down to less than an MeV, 1 MeV. So we're looking at precision of 10 to the minus 4. This is basically doing what LEP did to the standard model. The FCC would do to the Higgs sector and to the electroweak precision measurements. Same thing holds true for sine squared theta effective. Obviously, all of these parameters are very important, including the width to the B and mu1 and so on. But I just decided to highlight these 3 because they're the ones that are usually shown in various electroweak precision studies. As for the self-coupling, there's 2 ways of doing it. One is single H production or double H production. Single H production simply means you have to rely on loops. And that means that basically the sensitivity is not so great. So for example, if the self-coupling was off by a factor 2, in HH you'd have a 3% effect, in EE you have a 1% effect. However, HH production is much more sensitive, even though the production cross-section is only 1% of the total Higgs cross-section. And what that means is that one has to use differential measurements. And in EE, there's complementarity between Z in association with 2 Higgses. So here it is, a Z that creates here the 2 Higgses, and this is the vertex that we want, or VBF production, where you're probably not used to seeing the term VBF for EE collisions, but actually you can radiate the 2 Ws off of the 2 electrons, and again get a Higgs here and get a couple of Higgses at the end. And this is the 2 curves showing that the sensitivity is greater for the VBF production here and for the ZHH production on the other side, where this is the ratio with respect to the standard model. Looking at the full summary, the moment you turn on the FCC-HH, then by far the most sensitive measurements come from the di-Higgs production here, where it gets us down to basically 5% for the FCC program and something like a factor 2 higher for the ILC program. It goes without saying that the single H production is not as competitive as the di-Higgs program. So basically, self-coupling means 2H production. Now, let's turn now to what's left and let's look at beyond the standard model. Is the Higgs fundamental? We have effective field theories, and that's probably the best language in order to provide a feeling. This is not a very quantitative answer. It's a qualitative answer within factors of, let's say, factors of 2 or so, or perhaps factors of pi. Now, we have direct searches for beyond the standard model physics, where you basically start from specific models, okay? And these provide also information for precision measurements. Or you can decide to take the point of view that we really have no idea what the new interaction would look like. We write down all possible operators for something like this, and just the baryon and lepton number conserving ones at dimension 6 is over 50 operators, 53. So you write them all down. Obviously, we cannot now go through 53 operators, so we will just concentrate on basically these 4. So the first one is basically scaling all Higgs couplings by a common factor. This is almost like the kappa. The second one here, which goes as over coupling squared m star squared, I'll come to this in just a moment, is effective 4 fermion interactions, contact interactions, or the presence of a new resonance like a W prime or a Z prime. Here, you get 2 fermion, 2 boson contact interactions and the S parameter, and then eventually just modifications to the Yukawa couplings. And there's much, much, much more. But we will use these 3 in order to guide the analysis and what happens. Now, how should we think about it? Here is a reference. Think of the equivalent of like a pi-pi scattering that gives rise to a row. So in this case, a coupling between the Higgs and this sector, the Higgs now being composite, would be some coupling of G star. So then these 3 operators that we saw earlier on, which are the C phi over the lambda squared, they go as G squared over M squared. This is basically this thing here. I'm just copying the same numbers. The CW is 1 over M star squared, and this, the 2W, which is basically the 4 fermion effective or new resonances, 1 over G star M star squared. Now, it's important to remember these 3 rough dependencies. Incidentally, the coupling between the gauge sector and the rho is proportional to the gauge sector divided to the gauge coupling divided by G star. So, for a mass of a coupling of something like 2 TeV, the deviations are roughly 1% in the Higgs couplings. So then it's no surprise that if you then look at what type of limit you put on the compositeness scale on the x-axis here, and having seen that we get to sub% precisions here, the answer is that the FCC and click post HLLHC would give us limits up to about 4 TeV of scale over compositeness coupling. And the maximum sensitivities, of course, come out of these 2, the highest energy colliders. Probing a bit more to understand the direct versus indirect, let's concentrate on the plot on the right-hand side. Now, this looks complicated, but actually it's not as complicated as it looks. So first of all, you see this, these diagonal lines here. So this is the Higgs precision measurements, okay, which, as you saw previously, they go as G star over M star. So therefore, this being measured, this corresponds to a straight line between these 2. And that's why you get these limits. And here is click at 1500. Here is the FCC program. And with the dashed line slightly above that is click, the full click program. Then you have the vertical lines here, which is the OW operator, which is this guy here, which is the 2 fermion, 2 boson measurements. And as you see, it's independent of G star. And as a result, these are just vertical lines. And then finally, what you have falling like this are basically the searches that Now, the 4 fermion effective coupling or new resonances, they go 1 over G star M star. So the two of them are inversely proportional to each other, and you get this, this curve here. This blue is basically what the FCC-HH would get us. And then the dashed line that you see here is what click would effectively get in this region. You see that they're not very different, except that, of course, the FCC-HH offers higher reach in the G star over M star plane. You can reverse now this. And basically, you can say, what is the absolute limit on M star? In other words, what is the 1 over length of the Higgs? And plot this 1 over length here, which is the yellow bars that you see. The two ultimate ones that you can get is something like 15 TeV out of the FCC-HH program, the full FCC program, or something like 18 TeV out of click. HLLHC is down here, by the way. Okay, it's down by a factor of 3. You can also ask the question, which is how fine-tuned is this object? Keith explained all of this yesterday, so I don't need to go through it again. The traditional measure is to take the correction squared over mass Higgs squared, putting in the numbers, so it's a deviation from 500 GeV. So the high luminosity LHC would get us to this number here, this measure, if you use this measure, of delta greater than about 10. The FCC-HH, the direct limit, would get us to top quarks of about 5 TeV. So it translates to a limit of almost 90. A better measure can be expressed as this 1 over epsilon, which is the M star over G star. This is the vacuum expectation value, which just solving the equation, you can see that 1 over epsilon, which is the amount of fine tuning, is basically the measurement 1 over vacuum expectation value squared. And this is what we reach. We would get to something like 1 in 300. So a fine tuning of about 300, simply because of the Higgs being so light. This is about the ultimate reach for these future colliders. Now, what about direct searches like new resonances, contact interactions, and so on? There's two ways of seeing new resonances, particles, or forces. One is that you actually have enough energy and you produce it, and you have this beautiful here bright Wigner. That's called a major discovery. The other thing is that you don't have enough energy, so all you can observe is the tail starting to take off, and you basically, the rest of it is masked off for you by the collider that you have. The mass reach here for the direct is clearly the square root of S for the lepton colliders. For hadron colliders, a rough rule of thumb is something like a factor 3 to a factor 2 for weak couplings. If you go to deviations to high tails, you can actually now probe mass over coupling much, much greater than square root of S, simply because, as you can see, this object can be much higher, and yet you can feel the tail change. Hadron colliders are relevant for example, the coupling of the Z prime greater than the GSM couplings. So this is mass over coupling greater than about a half of the center of mass energy. This is what the reach would look like. This is a mass. Here is the effective GZ prime. Now, what type of Z prime? In this case, it is a very simple model. It's a universal Z prime. You will say, of course, the LHCb anomaly might prefer a certain generation for the Z prime coupling and so on. But this was done in order to not favor leptons or to favor hadron colliders and so on. So even though you can introduce flavor dependence, this is not here. These are the various lines. So you have the ILC, the high energy LHC, the ILC, FCC, and this is the result of the indirect searches as before. And then this limit here, the GZ prime over M, this is what you would probe directly at the FCC-HH. So this is the region where you can actually see the resonance because you produce it and you detect it. For the EE colliders, of course, this is all indirect effectively after the 3 TeV of the click center of mass energy. Contact interactions, you can take the Y and W parameters out of all the programs, and you can look at effectively where you reach in terms of Here is the O2W, and here is the OW, or also the B, of course, for the neutral. And what are the take-home messages here? The FCCHH has very comparable reach for the W and the Z, simply because via the Drell-Yan process, it can produce both equally. Whereas for the EE colliders, the Z prime, the Z, sorry, not Z prime, the Z reach is always higher than it is for the charged bosons. The sensitivity for EE colliders is of course enhanced for strong couplings, because strong couplings mean that basically you get a much larger effect and the thing is also wider, okay? And of course for W prime and charged fermion currents, you're much more effective at hadron colliders. What about extended scalar sectors? Well, the simplest thing you can do here is to introduce a singlet, okay? And here's a standard Higgs, here's a singlet that's been introduced, Majorana 1/2. So the two can actually mix. So the question is, down to what mixing would you have sensitivity? And throwing the entire kitchen sink, all the Higgs couplings and the electroweak precision observables, if you look at the limit on the angle sine squared gamma, where gamma is the mixing angle between the two states to get the two mass eigenstates, click 3 and FCC all are basically just about the same. If you want to talk about the direct searches, and you put here the 95% limit on sine squared gamma versus the mass of this new state, here is the ultimate best limit. This comes out of the FCC program. This is simply because here you're just using the vector boson fusion mode, so background and signal scale at about the same rate, whereas here you're dominated by glue-glue production, which is why it looks so funny for the FCCHH. This is one of the few, actually the only plot I have where you also see the muon collider for something like this, where the muon collider is here. All the EE colliders are further up. What about other extended scalar sectors? They're simply the purview of hadron colliders. So for example, if you take the two Higgs doublet models, like for example, we have in the MSSM, you can run a full set of searches at a hadron collider, which is associated BB bar production and the Higgses. And here you get BB bar to tau tau, top to BB, and that covers both ranges in terms of this parameter, which we call tangent beta. So if you look at the limit of tangent beta versus MA, the limits that you reach are somewhere between 7 and 10 TeV. And of course, they are an order of magnitude better than what you can get at an EE collider. Same thing holds true for the charged mode. So here there's basically no discussion. What about new particles in general? Well, if you want new particles, your best candidate is SUSY because it doubles them. So therefore, it's by far the most generous one for us. So the questions are here, if SUSY, this is a big if actually these days, which masses and mass differences of strongly or weakly coupled superpartners can we reach? Is nature fundamentally fine-tuned? If the solution is SUSY, how well can we test this? And is dark matter a thermal SUSY WIMP? All of this goes back to what SUSY solves for us, the hierarchy problem, the dark matter candidate, and so on. Again, for strongly interacting SUSY, gluinos and quarks, this is simply the business of the hadron colliders. And what you see on the left-hand side are gluinos. On the right-hand side, you see the top quarks. You see the various evolution of colliders, high luminosity LHC, high energy LHC. Low energy FCC is what if you had the tunnel, but the current magnets as opposed to the future magnets of the FCC. So the ultimate reach that you get here for the top quark is to get to something like 5 TeV. For gluinos, you can get up to masses of about 17 TeV. What does this buy us? Well, with respect to the high luminosity LHC, it would correspond to about a factor of 5. There's, of course, a very large number of analyses but it's probably not worth going through in specific details. When you see the bars going down, it's because the delta mass, the mass difference is assumed to go to low values, like here where it's only 10 GeV between the mass difference with respect to the LSP. Drawing more attention recently because of things such as G-2 and so on is the electroweak sector. So here in EE collisions, one can get to Chi2, Chi1 production, the neutral ones, and that means that you can actually run the Chi2 essentially to the kinematic limit of the collider, or the two charginos production, and you cover the entire space down to mass differences of about a GeV. For PP, you have to rely into the second lightest neutralino and the chargino, and you leave gaps at low delta M. So for example, here in the typical plot that has the masses of these two states, the second lightest neutralino and the chargino, here is the LSP. By definition, since this guy is the lightest one, this is kinematically forbidden. And the green line that you see here is what click gets to, which is essentially simply the square root of S divided by 2, period. Now, the FCC would get to something far larger that you see extends to more than a factor 2. However, you don't really cover these areas here. More on this in just a moment. By the way, this is what a Vino-like thermal dark matter would look like. This is the limit of about 2.8 TeV. So the EE sensitivity is independent of the nature of the LSP, okay? But you limit it to basically this number over here, and this is the extra triangle. The other big scenario is not Vino, but actually to go for Higgsino for the lightest state. And here, this is the limit that you get from click, which completely covers the Higgsino thermal WIMP case. The limit that you see down here, which actually exceeds this green line, that of click, is actually coming from the monojet searches, and this we will see in a moment, things like the broken track, stop track, and so on. When it comes to sleptons, the reach of click is basically, well, what else? Given by the kinematic threshold. For the FCCHH, it's actually off scale at about 3 TeV, so it's way to the right over here. What does it all mean? So obviously, it always comes back to, is SUSY natural? Now, we all know that SUSY is basically caught between the Higgs on one side and basically the direct searches on the other side, which don't quite see eye to eye. If you take the picture of natural SUSY and you start bumping things up to very, very high masses, what do you have to leave at the end? Well, Higgsinos are partners of this H, assuming that this mass parameter that we have in the MSSM with only one mu has to be close to the VEV, so Higgsinos have to be close. You need to have some colored particle which is not too far off, and then gluinos, and then Vinos. If you look at the corrections that these objects introduce to the Higgs mass, you get a fine-tuning from the stop mass and the fine-tuning for the gluino. Now the stop, because whatever the top does to the Higgs, the stop tries to correct it. So therefore, if this mass is too way off, then therefore this cancellation is not good enough. And the gluino enters simply because the stop is a spin 0 particle. So what does it feel? The correction from the spin 1/2. And who's the spin 1/2? It is the gluino. And that therefore, for a light stop, the gluino cannot be too heavy. So the two go hand in hand. What are the type of fine tunings that you would get to? So if you assume that you have very, very high scale, say at the gut scale for SUSY, you would have fine tunings at the level of 10 to the -4, 10 to the -5 from stop and gluino searches. For low scale mediation, it's at the per mil level. That's what you get from the full program. Incidentally, a question that comes up is what do you learn from indirect information? For example, if you let a new state run in here, and the answer is roughly 0.7% for each TeV for the new particle that's running in this loop. What about classic WIMPs? As we said, there are two SUSY extremes, pure Vino, pure Higgsino. The main tool for the pure Higgs Xeno is the stopped track, whereby this guy goes on, and then you get a pion out of it. And then the alternative is Electroweak Sector, where you basically feel it through loop parameters. So for the pure Higgs Xeno, both the ultimate machines, but primarily here the FCC HH exceed the 1.1 TeV, which is the limit for as long as dark matter is composed of one thing, and this would explain all of dark matter, because if you introduce now extra parameters, then obviously this disappears. And the alternative, if you look at the Electroweak Sectors in the loop, here, basically there's the Hadron Colliders cover completely the space. The EE program is basically far behind. This might overlap with the indirect detection experiments, where indirect detection, we mean the astrophysics ones. And here you well exceed the 2 TeV limit for the FCC. Now, sticking still to thermal WIMPs and so on, remember that the motivation for all of this is coming out of this WIMP miracle that basically says that the mass of the dark matter particle is something between a few GeV and up to, let's say, 10 TeV. Now, this miracle has been moving upwards to the TeV region, little by little by little. So for some of the searches that are going to be discussed now, we're looking at the GeV to TeV region, where you have two classes. One is a classic electroweak WIMP candidate, like what we just saw, and the other one is simplified models with mediator particles, both axial vector simplified models and scalar simplified models. So what about this dark sector? Very quick reminder, it spans a gigantic amount of mass space, okay? We know nothing about it, a total mystery. And the nightmare scenario is that this thing is totally dark and you only have gravity to play with. Well, the not so bad scenario is that it's not completely dark, but it's some shade of gray. I hear there's many tens of shades out there. So there you have direct detection or indirect detection experiments that come in astrophysics or colliders. So then thermal WIMPs here, you cover this region here of light dark matter, or the WIMPs, here is the Z mass to give you a feeling, okay? Whereby above these masses, you basically get too much dark matter. Below this, there are problems with baryon nucleosynthesis. And in addition, large structure formations and so on. Now, direct detection experiments, this is the limit from xenon 1T, the blue line here. This is a mass of the dark matter particle, and this is a cross-section. This shaded area is the infamous neutrino floor. This is where you start seeing neutrinos, because the cross-section has dropped now, the limit has dropped so low that finally you start seeing neutrino interactions and you actually have a background. Up to this line, theoretically, your only background is basically what it gets created instrumentally. Two-phase liquid xenon experiments have been increasing their sensitivity tremendously over the past few years. This is the most recent result from xenon 1T. The background rates that they get are incredible. And if you look at the next generation experiments, they will get us from xenon 1T down to, including this Darwin, Argo, they will get basically cover us all the way down to the neutrino floor. Below the 10 GeV region here, the GeV to 10 GeV, there's also a program for super CDMS. Actually, there's many other experiments as well. There's really a plethora of experiments. And then remember that this line here stops at the GeV. Now, if one takes a scale and moves it to the right, where now all of a sudden here are the GeV. So this is the one, the scale. So what we're seeing here is basically this part of the diagram. There's even a set of experiments, dedicated experiments being designed in order to cover this very, very light dark matter. There is an amazing creativity that these experiments are employing. This is a Sensei experiment that's using Skipper CCD, the Herald experiment, and so on, that are promising to basically, for Sensei here, the mass coverage is from 1 MeV all the way to a JEV. This is, remember that these lines here, the vertical ones, are threshold, and these lines here are driven by exposure and mass, so effectively total mass for the experiment. And then there are a whole number of direct detection experiments beyond WIMPs, like sub-GeV axions, axion-like particles, and so on, like the ADMX experiment that is trying to see the axion. The axion is the thing that would do away with this problem with the theta parameter being too low in the standard model for QCD. And it consists basically of a cavity, a high Q squared cavity, and then you read it out with superconducting with squids. And if you get a little blip as you tune the frequency here of the RF cavity, if you hit it just at the mass that would allow you to go through the Primakov effect to create the photon, then immediately you get a signal and you look for that signal and you don't get it. This is the only experiment, by the way, that has actually crossed the two thresholds of the boundaries of theory where the axion has to live. If you open up the scales, log 10, you see that here is the current experiments. The biggest new thing that is planned is this IAXO initiative that will cover down to basically 10 to the minus 11, and the prototype of it, which is the baby IAXO. And then you have some specific dedicated experiments to just specific mass regions. What about the colliders? What do they provide as information? Well, the effective coupling between matter and dark matter here, you can just break it up and put in a mediator. And if you do that, well, you basically just brought in a propagator. So now you exchanged your ignorance with the masses for two parameters. One is the mass of the mediator and the other one is the mass of the lightest particle. So the searches that are going on are, you can interpret all of the digest searches, all of the resonance searches in terms of an extra guy running in between the initial QQ bar state. Or you can interpret, you can use initial state radiation to get a jet, and then this guy going into unseen particles, and this would be for hadron colliders. For an EE collider, it's basically the monophoton signature. What is the type of reach that you get? Now here, there's a bit of trickery, because in order to get limits on the mass of the mediator, you need to assume some values here for the coupling. And of course, if you change this by a factor of 4, obviously you clobber the limit. Anyway, for the specific choices that you see written here, which is G dark matter of 1 and G coupling to the cube of a quarter, the FCC-HH is the one that has by far the largest reach in terms of the axial vector couplings. And then for scalars, okay, you have a higher coverage from click. In FCC-HH gets to only something like 2.5, 3 TeV. Summarizing it all, here is a rough picture of today with xenon 1T. Here are the expectations from the LHC. This is the same triangle as we saw before, except that now it's rotated, because this mass, this cross-section here, it's essentially the mass of the mediator. So it goes as 1 over mass squared in order to get the same units for cross-section. Okay, so this triangle advances, advances, advances. This is where the eventual limit would be from the direct dark matter experiment. What's the best thing that could happen to us is that nature has decided to land the dark matter somewhere in this region, because then we can study it both at the collider and at the direct detection experiments. If you, you can also, there are scenarios in which you can look at it in Higgs decays and so on, but I'll get to that if we have any time at the end, because there's still quite a bit to cover. Feebly interacting particles, this is a whole new frontier. It's very, very difficult to compare them, which is why typically there are these 4 portals: the dark photon portal, the dark Higgs portal, the axion portal, and the sterile neutrino. And from here, one identifies benchmark cases. I mean, needless to say, the parameter and analysis space here simply explodes. just to give you a feeling, these are the dark photon searches. Up here in mass of the A prime, this thing here is a TV. So clearly this is a purview of colliders. You also have some dedicated low mass searches, for example, from LHCb, whereby you search directly for the mu mu, or in D-star decays to D0 to EE. But this is only for a limited parameter space. And then over here, down here, this region is coming out of beam dump experiments. So Phaser, Methuselah, and potentially SHIP, if we're ever going to build something like SHIP. Let's go quickly now to the physics of flavor, lepton, and quark sectors. So there's neutrinos and the quark sector. Neutrinos, first of all. Remember that there used to be the invisible particle from Pontecorva, the cross-section of 10 to the minus 44 centimeters of an energy of 2 MeV. So this was considered to be a drama, that nobody would ever see it. Of course, he also calculated that you would get a few per day per ton with something like a 10 to the 11 neutrinos per square centimeter. And from these days, we're now at the level of talking about the PMMS matrix and CP violation. The basic tool here is mixing, whereby you start from a neutrino flavor A, you end up with a neutrino flavor B. And this mixing goes as well, the mixing parameter, and the sign squared that depends on delta M squared, the mass squared, length over E. And now, following this disaster for neutrinos, God blessed them with 3 major pluses. The first one is that you basically had the solar neutrino sighting, whereby from Super K and SNO, one observed large mixing, which meant excellent delta M, which is at the level of delta M squared of almost 10 to the minus 4 electron volt squared. Put it differently, it's basically MEV over 100 kilometers, which also meant that you could also have reactors to confirm the measurement. On the other side, Kamiokande, IMB, Sudan 2, Super K, and so on, they saw large mixing, again with super delta M. This is now for the atmospheric neutrinos, where this delta M happens to be very different from this delta M, but still the value that comes out of atmospheric neutrinos is a JeV per 100 kilometers. Now what that means is that you can do this physics with accelerators, and that gave birth to K2K, MINOS, NOVA, and the short baseline experiments. The summary, of course, is that you can decouple these 3. These are not 100%, but essentially they drive these 3 phenomena. So one matrix here is the atmospheric and the accelerator disappearance. Here are the short baseline experiments and the accelerator appearance. And then finally solar and CAMLAT. And you can also have overall phases. So first mystery is this, and in particular, whether we can see the phase. Second mystery is that what you get out of here is delta M squared, but you have no idea whether the third neutron, these two are very close to each other because of the known values that we have here. This one is actually very, very small. So therefore, nu1 and nu2 are very close to each other, but what we don't know whether nu3 is on top of these guys or below. So these are the things. So these were the 2 major blessings. And then came a third one, which is in the measurement of θ13 in diabase. Here is a measurement, the neutrino, they start from a neutrino beam, they measure the neutrino beam, and basically there's a deficit that you actually see here. And the measurement that comes out of this is for a large θ13. So this is the third lucky strike, which basically means that if you look at CP violation, it is basically 3 times 10 to, 3% sign of delta CP to be compared with that in the quark sector. So neutrinos were blessed 3 times subsequent to the very, very low cross sections. Where do we stand today? Essentially, we're in the precision era for all of these parameters, because if you look at the right-hand side of the 3 sigma range for their values, we're looking at basically a few percent, maximum 10% of things like delta M squared. Okay, but typically it's around the percent level. So this is the picture today. Now, what happens in the future? Well, you want to measure delta CP, as we said, in the mass hierarchy. The simple equation that we saw earlier blows up to this beast over here that now takes matter effects into account. And this is for nu mu to convert into nu e. In principle, if you had everything under control, you could just measure nu mu to nu e and nu mu bar to nu e bar, and the difference between the two would give you a CP violation. Now, in reality, there's many unknowns, and in particular, the parameter A that also brings in the effects of matter effects into account. This is where the complementarity between the Japanese program and Fermilab is extremely useful, because Fermilab is the 1,300 kilometers. The Japanese experiment is at 200 kilometers. NOVA is at 800 right now. So it means that they feel to a different extent the matter effect. Now, currently there's a small disagreement between NOVA and T2K with a small favoring of an angle of minus 90 degrees, 3 pi over 2 for delta CP. If that were true, that would be the fourth lucky strike, because delta CP, meaning that the CP asymmetry being the sign of this thing, would be maximum. So talk about being lucky here. Now, if you look at these fits, they're actually very, very complicated. So it's no wonder that right now the situation is a bit confused. So this is a leading term out of theta 1,3. And then you have 3 more effects. Here is the matter effect, which would be different between the 2 experiments. The CP conserving effect, which is the green line, and the red line, which is the CP violating effect. All of these are drawn for maximal CP violation of pi½ What is the reach of these future experiments? So concentrating on the current program for T2K2, what you see is that here is the true delta CP angle. You would actually, if we were so lucky that delta CP would be at 3 pi halves, we would actually get a better than 3 sigma observation already with the T2K2 program. This is if you don't know the mass ordering. If you know the mass ordering, you actually get it on both maximal values out of T2K2. What does the future, the long-term future hold? So on the one hand, you have June in the US, and the other one, Hyper K in Japan. This is the reach in delta CP as a function of number of years. Here is Hyper K with a hypothetical start at 2027. And what you see is that both actually exceed for a value of delta CP of pi halves or 3 pi halves. They can actually discover with 5 sigma CP violation within something like 7 years or so. Hyper K has a much larger uncertainty here. More on this later if you want. The incredible thing also is that Dune, because of the long baseline, can actually cover also the mass ordering between the states. And this is the delta chi squared, and irrespective of delta CP, irrespective of its value, you can always get a 5 sigma measurement if not a 15 sigma measurement, if you're sitting at the right delta CP, at the best delta CP of the mass hierarchy. Very useful and nice here is the complementarity of the program, and of course the detection technique. In one case you have a liquid scintillator, in the other case you have water Cherenkov, and therefore the systematics would be very different and so on. Majorana versus Dirac, there is a huge list of experiments that are looking for neutrinoless double beta decay. Here is an example from Kamlan Zen. Here is the energy of the electron measured, and what you have, this is a region where the neutrinoless double beta decay would actually show up. They have something like 8 events, signal of 3. They correspond to a lifetime of greater than 410 to the 25. This number will essentially get to something like 10 to the 28. For example, here's the EXO experiment. The NEXO, which is the ultimate version at 5 tons, would get us to 10 to the 28 lifetime. Mass limits, direct ones. The best ones come from astrophysics measurements, the baryon acoustic observations, and the structure formation. The total mass gets us down to a 1/10 of an MeV today. The ultimate is to get, this number is here, is to get down by an order of magnitude. And then direct neutrino mass limits. The best one comes out of Katrine. It came out Last year, it gives a limit of 1 electron volt. It's a usual Curie plot. This is the energy of the emitted electron, and you're trying to see deviations at the very, very tail of this object. The ultimate that you can get here is shown at the bottom, which is the Project 8 experiment they have employed. They have demonstrated a completely new technique, which is based on the detection of cyclotron radiation emission spectroscopy, which would allow them, with usage of atomic tritium, not molecular one, because with molecular one, you get a little fuzzy line because of the, well, it's 2 of them, whereas with atomic, you only have 1 guy decaying, of something like 40 MeV. This would be the ultimate limit that would currently be planned for these guys. What about the Quark sector? Well, remember that the Quark sector has been probing this infamous VCKM. Here is a 3x3 matrix. It has to be unitary, which means that you satisfy 6 equations beyond the diagonal ones of this form, and you therefore have 6 triangles. This is just the generalities for the academic training. Now, we are so lucky in this case that the BD triangle is the 3 sides are roughly of the same side, as opposed to the chaonic one, which is sort of very elongated, and therefore CP violation is a very, very small effect. So what it means here is that what we do is that we take this triangle, divide by 1 side, which is VCB over VCB, and you try to measure the 3 angles and, of course, the 3 sides. And this is shown here. This is where we stand today. This is where we would be in only 4 years from now. And this is where we will be in 2035. So beyond, even before any extensions from the FCC program and so on, the precision that would be attained in this sector would be totally a huge improvement over today. It would just test this thing at the level of per mil, basically. Now, there's a very rich B&D program, which is planned by Bell2 and LHCb, and some of it also by Atlas and CMS in the next 10 years. What are the big observables? One is the 3rd angle, gamma CKM, which is the angle here, which is supposed to be the tough one of these 2. This one is basically things like Psyche short. This one is charmless decays, B2 pi pi, B2 KK. And this one here is the decay type modes. So the angle gamma, to get better precision on that, the phase on B sub S mixing, the phase in D CP violation, and then, of course, very rare decays like B sub D and B sub S. The most recent result here is a beautiful measurement by LHCb of the CP asymmetry in the D0 decaying into 2 CP eigenstates. They have a 5 sigma observation, an asymmetry of less than a per mil here, well, 2 per mil, okay? If you look at how this would evolve over the next 5 to 10 years, over all the decay modes of delta ACP, and if we assume that LHCb gets its ultimate upgrade, then the phi, the phase of the D decay versus the Q over P, which is the magnitude, the 2 amplitudes, would shrink from the current blue to basically this tiny little red here. So it's, yeah, precision physics. B sub S, B sub D to mu mu. This is a current observation from LHCb. We haven't yet seen the B sub D, but if you look at the branching ratios of the 2 in the future program, you see that one would actually narrow it down here. These are the future measurements to an incredible value. And certainly one would be able to test whether the B sub S is slightly off with respect to theory or not, like we suspect. You've obviously heard a lot of noise about flavor physics in the quark sector. There's lots of attention on lepton universality. It all comes from comparing mu mu k decays to EEK decays of B mesons, okay, or K stars, the same thing. The idea is that they come out of loop diagrams like this because the Z cannot couple between the B and the S in the standard model, so it can only go through loops. The point is that these 2 leptons are coming out of this vertex. This is purely electroweak, so therefore it doesn't depend on the strong correction. So when you compare muons to electrons, you should be able to have a very, very precise prediction. Make a long story short, The most recent measurements of this RK value, instead of giving a value of 1, essentially between electrons and muons, it gives a value which is off by 3 sigma. There was even a workshop here, flavor anomaly workshop, FAW21, I abbreviated it so it fits in here. Here is an unpaid ad, so you can look at the many beautiful talks that were in there. This is a global fit of all the observables, because beyond what you see here, there's also the angular distributions, there's the semi-leptonic decays and so on. The agreement between all of them is not so good. The C9 and C10 are the corresponding Wilson coefficients in the most general expression of B decays. However, if you limit yourself to just the lepton flavor universality and the B sub S to mu mu, there's actually quite a bit of agreement between the different measurements, and this is a current deviation. What does it mean in terms of direct searches? In this very, very recent talk, there's 2 types of classes. One of the biggest explanations would be a scalar leptoquark, whereby you simply have something here that gives you the muons and couples directly to the quarks, running in this fashion between the B and the S. So the mass regions would be something like 10 to the 3rd to 10 to the 4th for scalar and vector. And here is the ultimate limit that you would expect, say, on leptoquarks out of the FCC collider, okay, and you would get to something like 4.5 TeV, okay, this would be click. This is a coupling parameter of over the mass. Essentially, you would probe much of this thing directly if nature would be so kind as this new object, if this observation stands the test of statistics. Other flavor physics in the quark sector, extremely important to measure, are rare kaon decays. We've had the observation of K plus to pi plus mu bar last year at the branching ratio of 10 to the minus 10 out of Na62. This has been a triumph. This has been a program that's been going on for more than 20 years. If one compares the other decay, which is the K long going to pi 0 nu bar versus K plus to pi plus nu bar, this one is currently still not observed by the Koto experiment in Japan. Their sensitivity is still a factor of 2 worse than the standard model. If we extrapolate into what we expect in the future, this is the current Na62, the measurement of pi plus. This would be a guess of what Na62 can get on its own. And then Koto 2, and then there's a clever, that's actually the name of the experiment, proposal at CERN that would actually narrow down the error bar on pi 0 to nu bar to the level that you see here. I drew these by hand. Flavor changing neutral currents in top decays. So here, for things like top going to gamma charm, gamma U, gamma quark, the FCC HH is unparalleled. And then flavor changing neutral currents with Higgs decays, okay? Here the program, this is the branching ratio, the upper bound that you get top to C Higgs, U Higgs, or then tau mu and tau E. The best type of sensitivity you get on these branching fractions are to charm and Higgs, and you get to better than almost 10 to the minus 5. This is the best you can get. Now, the overall picture of what it is, you have to supplement it with the physics of charged leptons. So for example, mu to E gamma decays. There's been no update from the MEG experiment since 2016. However, there's a whole slew of experiments which are currently in progress. MEG2, mu to E, comet, mu through E. They use all 3 detection techniques for this flavor violation, mu to E gamma to 3 electrons, or muon absorption and then seeing an electron coming out of it. On the time axis, we expect over the next 10 years, this is the branching ratio, to go deep into a region of at least a factor 10 or a factor even 100 in one case better than where we are today. One thing of very that's really worth mentioning is that Bell 2, incidentally, will be a tau factory. They expect 5 times 10 to the 10 tau events, which means that they can actually probe tau to 3 muon decays. This is where we stand, so they can improve it by more than 2 orders of magnitude. Absolute qualitative summary of observable versus the scale. So here is where you have the kaon and the B physics. Here is the charged lepton sector. Here are, we simply no time to discuss neutron electron dipole moment and neutron dipole moment, and then Higgs flavor changing decays, top flavor changing decays, and then direct searches and electroweak precision. Take home message, the direct ones are nowhere near in terms of reach of what these indirect measurements give us. But the problem with the indirect is the word indirect. Pseudo summary, and I'm really sorry that I took longer than anticipated. There's an extremely rich future for HEP, as long as a couple or at least one new machine are or is approved and put in motion in the near future. All options for a Higgs factory bring us to the level of a percent or 10 to the minus 3. This is supposed to be a power understanding of the couplings. Important aspects are a precision program, electroweak precision program, which would need the next generation Z factory, and also running at the top threshold. And actually, the linear and circular options are quite complementary. So if it would be at all possible to have both the circular and the linear collider, that would be beyond beautiful, BB physics. Fundamental scalar, you can probe it to something like 15 to 18 TeV. High energy EE and PP colliders, supplementary information. And then the FCC combination has simply the largest direct search to new particles and phenomena, from new particles to Higgs self-coupling to dark matter searches and so on. Dark matter, a whole slew of direct detection experiments continue to improve their sensitivity. They will get to the neutrino cross-section floor. Let's not call it, there's complementarity between indirect searches and colliders, and the next-gen colliders will cover the thermal WIMP scenario completely, as long as there's one type. Flavor physics, neutrinos have all that one could possibly ask of them, okay, albeit a small cross-section, as long as this delta CP stays at about 90 degrees, minus 90 degrees. In the next 5 to 10 years, we could get very pleasant news from the T2K program, and the definitive statement of mass hierarchy and CP would come from the full program, Dune and Hyper-K. Again, complementarity is important here. Quark sector, the current situation, what I showed with the lepton flavor universality, will be completely resolved in the next 5 years, because the measurements that we expect in statistics will shrink, will either take this 3 sigma and turn it into 5 sigma, and then we know that we're after something, or we'll bring it to the standard model. If the current small deviations are confirmed, we will have the first experimental evidence for new physics from the current collider HEP program. The KON program is complementary. There's very important ongoing experiments on charged lepton flavor violation. So it is, if you look at this, it is really the best of times. It's not the worst of times. It is the times of wisdom. It's not the times of foolishness and so on and so on. Enough of Charles. As long as there's an international move soon towards a new collider. The physics that's ahead of us is simply extremely rich. Thank you, and apologies for taking longer.
Aris, thank you very, very much for this detailed and highly instructive lecture, including all the updates that you have put in after the update of the European strategy in 2020. The floor is open for discussion, and I would like to ask the participants to raise their hands via the Zoom feature, and then I will unmute. So I have a question by Tanya Robbins.
Okay, I hope I'm unmuted.
Yes.
Very good. Okay, thanks a lot for this talk. I have a comment. Unfortunately, we don't have the slides yet, so I don't remember the slide number, but it's on the extended Higgs sector discussion. I mean, you said righteously that a lot of these sectors can be probed, of course, at hadron colliders. But I mean, you also have constructions with extended scalar sectors. Yeah, so for example, the MSSM, yeah. But you also have examples where you have purely electroweak interactions where the additional scalars don't couple to leptons, for example. And there, I think one should not forget the importance of lepton colliders. So it's just a comment that, yeah, this is nice, but there are scenarios where, in fact, the plus and minus or muon colliders would be better than hadron colliders due to this, let's say, electroweak production processes. Okay.
Of course, I agree completely. I mean, just like in everything that I showed when I was showing universal Z prime model and so on, one can always now start taking these models and turning them into fermiophobic models or and so on, that would turn off couplings to one side completely or raise the couplings to the other, and that would immediately make one visible in one case and invisible in the other case. So clearly, for very specific models, theory is very creative.
Yeah, okay. I mean, I think it's a broad class of models which obeys this. So it's just a comment. I think we agree. Okay, thank you.
So are there further questions? Please raise your hands. Maria. Maria Dimu.
Am I unmuted
Yes.
now? So thank you very much, Paris. You talk clearly and with enthusiasm. This is the least technical question. Excuse my ignorance. I stopped physics with my graduation already. You spoke in the conclusions, there was a bullet on dark matter with equal enthusiasm, and I cannot remember in which slide you probably elaborated, if you did, but the layman off the street says that our equipment, even with evolution of technology or modern accelerators, etc., eventually will have difficulty to actually observe experimentally dark matter, and that it is very catchy and we use it systematically, but we should be lucid and don't hope very much for it. What do you say about this? Again, sorry if this is really a question that is not expert enough.
All I can say is that up until, say, 10 years ago, these lines that you see here, which are the detection experiments, on the left-hand side, it appeared that it would be extremely difficult, if not impossible, to really lower the thresholds. And since that time, there have been at least 3 techniques that have been invented that allows people to actually go to the left. Okay, so to some extent, what is shown is what experiments, letter of intents, TDRs, and so on show. And as you know, they're all subjected to very detailed reviews by many, many committees that ask, but are you not being super optimistic here? Are you not being super optimistic there? So therefore, people, I think in many cases, understate what they can do. And eventually the experiment delivers more than it actually can. I think that, for example, in the case of the HLLHC, we may get to even better measurements than what we expect right now, especially in the double Higgs sector. Having said that, what has happened is that we've been pushing this frontier to the left. How? With basically ingenuity. And if you look at this region here, where now we're talking about tens and hundreds of MeV, this is completely new space, which 10 years ago simply did not exist. So indeed, it's true that, if dark matter is an order of magnitude below here, the neutrino floor at this mass, or if it's down here, it would be very, very difficult to detect it with what we see today. Just like SUSY, if it's at 100 TeV, everything we showed today would be basically off the table. But to come back to a more optimistic scenario, what we can cover with the currently planned set of experiments is a huge improvement over 2 orders of magnitude here, okay, over more than an order of magnitude on the low side, And extending then to MEV regions, we really, there's a host of experiments actually, not just one. This is but one example that are beginning to probe this region. R&D and funding.
Thank you very much.
Sure. Let me, in the meantime, upload my, I apologize. I thought I had done it because we had a little test prior to the.
Yes, it's not yet on Indico.
Yeah, because I pressed on choose from your computer, but then I never actually pressed the other button. Hold on, upload.
Let me also say, Paris, your last comment sounds so beautiful that it could be like the final word of these lectures. But if there are people who want to raise their hands to ask further questions, they are invited to do so. We still have a bit of time.
So they are up there.
So the talk is up. I have a raised hand feature from Kurt Hübner. I ask you to unmute. I hope you are unmuted.
Thanks, Paris, for this very nice lecture. I have one question, maybe I missed it. It is important. How is it important for the time it takes to these positions that there's a difference? The linear collider has only one experiment, and the circular colliders have more than one experiment. What is the importance of this?
With apologies for the pun that is coming up. Yeah, I think that, or maybe I should skip it. I think having two experiments is extremely important, having more than one experiment. Remember that to this day, out of the combined LEP and the 4 LEP experiments in SLD, there are measurements that have to do with asymmetries like left-right asymmetry and so on, that are in disagreement between the two sets of experiments. And we don't have an independent measurement of, for example, the left-right asymmetry with a polarized beam. That would be really great to have, but we don't. So having only one experiment, there's always that lingering thing that you would like an independent confirmation with a different detection technique and so on. I will not enter at all into the socio-economic aspect of having only one experiment instead of two. And only one person writing recommendation letters for everybody. That would be another one, another aspect. Having a single experiment would put us into a corner. Now, there are, of course, plans for moving in and out with two different experiments. And then it's up to the program committees to decide, you know, who goes in first, who goes in second, and then how they publish in what order, and so on and so on. But that's next to leading order effects. Having a single experiment is not pleasant. I'm showing that I'm polarized right now. If I'm allowed the joke.
Thank you, Paris.
Okay.
It's a pleasure to hear you, Kurt.
Real pleasure to hear you, Paris.
Indeed, if I see no more hands, then I can just reiterate the pleasure of having had this talk. Paris, thank you very much. This would be an invaluable resource that we put on the academic training website. And I thank you very much for the effort and the enthusiasm that you have put into this lecture. Thank you very much.
My pleasure. Take care,
I
everybody.
close the recording. Bye.
Bye-bye.